Okay, so today what I'm going to do is basically set the screen for, not screen, set the scene for um, uh, radiative processes, particular radiative processes that will come in the next few days. Okay, and then in the next 3 days, I will try to do three radiative processes, but I mean, it may not be, I may hurry through some of them. Unfortunately, we do not have too much of time. So the three radiative processes that I will do is um, the synchrotron radiation, X-ray, this Bremsstrahlung, and Cherenkov. But to do that, I need to sort of prepare the scene a bit, and that's what I'm going to do today. Okay. So as we started like last time, I have actually written down the notes beforehand so that things go a little faster. And at this stage, you have been looking at this kind of formalism for quite some time, so it should not be very difficult for you to pick up. Because once I finish today's lecture, I'm going to upload it, and that will be form the basis of everything that I've done about radiation. And the next lecture uploaded will be when I will do Cherenkov and others. Okay. So last time we did this nice extension of the dipole radiation, where we showed that if we expand the far field approximation, take into account the second term in the approximation, which is this 1 by c n cap dot r prime, then we have another component to the dipole radiation, which was coming from the magnetic dipole instead of the electric dipole. So that gives you the full dipole radiation formula. Remember, this is still dipole radiation. Then you can have quadrupole radiation and stuff. Today, I'm going to basically go beyond this kind of radiation that we talked about, the dipole radiation, and go to the general radiation formula, the flux emitted. And over there, our aim would be to come to some sort of arrangement where we can write down the flux in terms of some averaged quantity. So basically develop the formalism for an average flux. Okay, so that's my plan. So that's what I'm going to do today. So let us start by a little bit of recap. So remember, we basically did the expansion, the extension of the Green's formula for not only space, so not only R, but also with T, where we had this box square of GR. So this is things that we did before, which was given in terms of two delta function. One delta function was basically the delta function related to the spatial dimension, and then there was the time delta function. Okay, and if you remember, we could basically write down the delta function in time as in the notation of a delta function in terms of an exponential. Okay, where now the time comes with a frequency, so it's an integral over d omega. I'm basically doing a very quick recap. And then there was the other part, which was the delta function of r minus r prime. That was written in terms of our differential equation, which was minus grad squared omega squared by c squared, where we introduced this g omega, this thing, where this g omega was basically related to the real time, real space thing, gr, in terms of this integral. So this is what we have done before. Okay. And after some process, we found out that the form of this g r minus r prime t t minus t prime, this was basically in terms of So over here, of course, we have multiplied the t and the r part. And when we solved for it, we found that this was in terms of a retarded Green's function. So the solution to this equation, was the retarded Green's function. Okay, and we took the retarded Green's function, where when it was not retarded Green's function, where there was no movement, where there was no acceleration, your solution was just 1 upon r minus r prime. That was just the solution. That's basically the electrostatic solution. But then when we have a charges moving, we have to take into account the retarded time, which was like this. So this was the formalism, and we immediately use this formalism over here. So we use this formalism to write down in the Lorentz gauge the solution for the scalar and the vector potential. So remember, we use the Lorentz gauge. In the Lorentz gauge, we actually had equations which are reminiscent of this equation for both the scalar and the vector potential, right? We had this 4-dimensional Green's function kind of equation. So there was this 4-dimensional scalar equation for the scalar, and there was the equation for the vector potential, and basically use this technique to write down the solution for the scalar potential and the vector potential. This we have done in full detail before, so till now everything should be familiar to you, or you can go back and look it up. Okay, so when we do it for the phi, again it is an integral over the source position, integral over the time, and then there is this delta function which gives you the retarded time, and then because phi is an integral over the charge density at the source position. So this is in terms of r prime. Okay. Similarly, for the vector potential, and I should write the vector potential over here. Okay. Similarly, for the vector potential, it's the same integral over the source and the time dt prime. These are at the sources. Primes are source and unprimed are field position. And instead of a rho, we have 1 by c, the current density. Okay. This is what we got. This is the solution that we have. So now we use this above formalism to integrate over t prime. Okay, we have to integrate over t prime, and so we use this formalism to integrate over t prime. We use this kind of formalism. Okay, so use the formalism of delta to bring in this exponential and integrate over t prime. So first realize that when we integrate over t prime, we will basically have the equivalent in the frequency space. So if there is a function in the t space, the time domain, will have a Fourier transform, the equivalent in the frequency domain. And those two functions, this f omega and ft prime, will be related by these two equations, where this f omega will be an integral over dt prime, because we have to integrate over t prime, right, of ft prime, when you multiply by e omega t. And similarly, we have to normalize it and get ft prime in terms of f omega. So these two will be the two time frequency domain equations that we'll have. And so what we will have basically is that for your potentials, which are the potentials over here in terms of r and t, we will have the potential in terms of r and omega. So we'll go from the time domain of both the scalar and the vector potential to the frequency domain. Okay, so every phi r and t and every a r and t, they will go and give and phi r and omega and a r and omega. Okay, this is what we should get. Over here also I should put in a vector sign. So we can do this, and if we do this, so this is exactly what we have done above. We will see that what we have is, remember, we have e to the power I omega t minus t prime, right? And that delta is in terms of this lower quantity over here. So look at this part and then look at this part. And so accordingly, we will have an I omega r minus r prime by c. That was the t part, because remember t prime is equal to t minus r prime by c, right? So we have to have this equivalent form over here. So your phi r omega, we'll get it basically. So instead of a phi rt, if I go to the frequency domain, then we will get these two formulas for phi and a. Okay, where the density, the charge density, and the 1 by c current density, these are multiplied by this exponential by r, basically. So these are multiplied by this e to the power I omega r minus r prime by c, and then there is always this r minus r prime modulus sitting. So 1 by r basically sitting at the denominator. So these two will come over here. Okay. This is straightforward to do. So we end up with these two equations, which are in the frequency domain. Okay, for both the scalar potential and the vector potential. I'm going a little fast. If I have written down, of course, you would have probably, I don't know how many of you write down notes, but then it will be good to see this. But this is straightforward till now. Now, before we proceed, we have to make one more observation. So my f of t, it is real, of course, because we measure it, because it's in real time, we know what it is. So because it is real, it imposes the condition on f of omega. Okay. The condition that it imposes is that f omega star is f of minus omega. That's the condition it imposes. So this tells us if I have this f omega is conjugate is the same of f of minus omega, just because f of t in the real time, the function is a real function, it's not complex, we measure it. Okay. That tells me that my power spectrum in omega space, which is f omega modulus squared, that comes from f omega star times f omega, that is the same as f of minus omega times f omega. So this is what we get from this observation, that f of t is real. Okay. So this f omega star, this f omega modulus squared, this power spectrum, first of all, that is a real number now again. And as you can see, it is symmetric when I go from omega to minus omega, so it does not matter. Okay. So the sign of omega is not very important. What comes in the physics is basically the magnitude of omega. It's the magnitude of omega that determines the physics. Because at the end of it, I'm interested basically with the modulus of f omega squared, because basically interested with the power. And over there, the magnitude comes. Okay. So now we go through very similar steps that before, is we introduce this.
So can you explain the third point again? That why the sign is not important?
Because at the end of it, we are basically interested in powers, and powers are always squares. So your final answer will always be basically, you will see, will be in f omega modulus squared. In that term, you will get.
Okay. Yeah, fine.
So in the next step, okay, we introduce this thing which we have done before. So basically, we look at the r minus r prime and expand it, and we can write it as r minus n cap dot r prime. Okay. This was easy because it's just like a triangle, and you basically drop the two sides are very long, one side is short, and drop the slightly shorter of the two long sides onto the long side. That's what it is. So that's the, and then of course we have these higher orders which we did not calculate. So remember, whatever we have done before, if we wanted to, we could have gone into the previous case, we could have gone into this 1 by r squared terms, and we could have calculated higher order terms. It will just be very, very small, and we do not bother with it. But if some problem demands that we go to higher order, then we have to calculate the higher orders. So we don't really require most of the time. So then what we do is this in r minus r prime, wherever we have this quantity, which is the quantity that we have over here as in the exponential as well as at the denominator, we are going to put in this this simplified form. Okay, and so this exponential obviously will separate into two exponentials, which you have seen before. Right? So the exponential is separated into two exponential, and we will basically have this.
Sir,
Yes.
in the equation r minus r prime, there should be a modulus of r, right?
This is R. Yes, this is a scalar equation. Yes. Hold on. Thank you. Let's get rid of oops. Yes. Thanks, Victoria. Sometimes I, when I write down, I don't. Thanks for pointing out all these things all the time. Yeah. Obviously, yeah. Anyway, so then in this asymptotic limit, okay, we will have the asymptotic limit of the two potentials phi and a. Obviously, it will now have two parts to it, one corresponding to this first part r, and another corresponding to the second part. So it will break, and as you can see, what will happen is we will get the phi and a in terms of this. So there is this first part, okay, in both the cases, which is e to the power I omega.
Sir, so the argument of rho and j should be r prime, I guess.
Argument of rho and j should be r prime. I agree. The argument of rho and j should be r prime. Okay. Okay, good. So we have this two, where there is this first part, which is exponential of e to the power I omega r by c by r. Okay. And then, of course, we have the second part where this n cap r prime term comes. And we have to, of course, integrate it. And obviously, you know this before, that the second term, this term is basically, so the first term is basically looking at, in some sense, the potential as a function only of the distance, not taking care about what is happening within the system. And the second term basically takes into care about what is happening within the system. But now, of course, everything is in the frequency domain. We are not doing in the time domain. Everything is in the frequency domain. So we have whatever you have done in the time domain, we are redoing it in the frequency domain. Now, if you look at the exponential within the integral, then it has this omega n cap dot r prime, okay, dot r prime by c, and omega is basically 1 by lambda. Omega by c is 1 by, basically lambda comes over here. So n cap r is, in some sense, is the size of the system, right? And so what you see over here is what you have is the size of the system divided by some radiation wavelength. Okay. Okay. And so that, in some sense, tells you when this part is important. If your radiation wavelength is smaller than the size of the system, obviously this plot will be important. If the radiation wavelength is much larger than the size of the system, then it will be very close to zero, and so it's not very important. The other thing is that over here we also have a propagation vector. So omega n cap by c is basically k cap, which is the propagation vector. So we have the propagation vector. So this whatever is in this exponential is basically k cap dot r prime now, both the cases. Okay. So now, as you can see, these two equations I can write like an equation like this, where I have a phi, the scalar potential or the vector potential, which is a function of r and omega, so in the frequency domain, is basically e to the power, so there is the long distance term, which is e to the power I omega r by c by r, times rho and 1 by cj. So you can write this over here. But this rho or 1 by cj, for example, these are just like this. So basically it's k dot r prime, the exponential over here. So similarly, I have just written for rho, I could have written for a also. Okay. So this is the structure of the equation, which connects basically rho and j, which is in terms of the propagation vector and frequency, to the phi, which is in terms of the position and frequency, or a, which is in terms of position and frequency. This is the connection. Okay, so this is something that we should keep in mind. Right. So with this now, so we have what we have done now. So if you go back, we have basically started with the solution of the four-dimensional Green's function. Found that in the Lorentz gauge, the phi and the a, they could be basically solved using a four-dimensional Green's function. Found the phi and the a in t and r, and then we basically went from the t, from time domain, to the frequency domain, and found finally that your phi and a can be written in terms of two terms. One term which depends on the r, the other term which depends on the propagation vector k and the frequency. Okay, so that's what we have come to. So now, of course, what we want to do is, once we get phi and a, we want to calculate my b and the e, okay, the two vectors. This is the same thing every time we do this. This is standard in all of EM. We find phi and a and we calculate the field vectors, and we use basically the Maxwell's laws. Since we are doing in the frequency domain, you realize that my del del t, wherever there is a del del t, I can replace it by a minus I omega. And wherever there is a grad, I will replace it by a I k cap. Okay. So these are the two replacements that will go in. Okay. When I'm going to calculate my b and the e. So wherever there's a grad, I will put in I k cap in front. Wherever there's a del del t, I will put a minus I omega in front. Okay. And this I k cap and I omega, they will basically come along with these equations. So you do that, and we end up with this equation for the electric field and the magnetic field. Okay. So electric field, remember, has a 1 by c. So there are two terms of the electric field. And so we write it down like this. And the magnetic field, so over here, it's minus del A del T is this first term. So remember, this del A del T gives you 1 by c j k omega. This term comes from del A del T. Okay. And this term comes from phi because it has this rho in it. Right? So this is how we write down the electric field, these two terms. Okay. Along with the I omega and I k. And k, remember, was omega by c plus n cap. So whenever I have a k, I can write down as omega by c. N cap. So this is what we basically use. So this thing and this thing, both on this, gives me my E. Similarly for B, it is basically curl of A. So I know what is A. I know what is A from over here. So this A I know in terms of e to the power I omega r by c. This equation that you can see on the top of the page, that gives me my A. I have a curl, so I get an ik, but k is basically, remember, omega by c into n. So this is what gives me my I omega by c, and then there is this n is still there. I omega by c n cap, remember. So the curl gives n cap times j cap. So this is how it is. Now we have this equation for my E and my B. Okay, these two terms. I'm quite happy I'm doing it like this because I'm going very fast. If I've written all these things down, I would have taken, I mean, it's good in some sense. I know if you write it down slowly, I mean, for some of you, maybe you can follow it like this. For some of you, maybe it's more difficult to follow when I scroll through pages. If I write down, it's easier, but you know, yeah, I would have spent half an hour writing what you have done till now. So I'm quite happy that I wrote it down before. Now, when we have this equation for the electric field, it has two terms, right? What we can do is that we can use the local charge conservation equation over here. So if you have the local charge conservation equation over here, then del rho del T is divergence of J, and that gives me this equation in the Fourier domain, in the frequency domain. That is your omega times rho is K dot J. Okay. So remember over here in the first term, I have sort of put some circle in the first term, in the sense, in the equation for E. If you look at the second term in the equation for E, I have put a circle in omega and a circle in rho. So we have this omega rho. So I can replace that by K dot J. Okay. When I replace that by K dot J, then I have an n cap K dot J, right? So I have this omega rho. I will have one rho from over here. Sorry. I have a rho from over here and an omega over here, right? And so I can replace that. That will give you K dot J, and there's an n cap there already. So we'll have an n cap K dot J. Okay, that term will come. So we can eliminate the second term and write my equation of E in just one term equation. Okay, so we can rewrite this second term. I can write it as a one term, which will give you an n cap term together. Okay. So write it like this. So I'm not going to do this steps. So you can write it in one term, and then I'll simplify a bit more. And when you simplify a bit more, you'll find that you have come to this obvious conclusion that your electric field anyway is given by these two terms. So you have calculated the electric field in the frequency domain at any position and the magnetic field at any position. But you also come to this obvious conclusion that electric field in the frequency domain is minus n cap times magnetic field in the frequency domain, which is of course is obvious, because this is exactly what it should have been, because it was also there in the time domain, right? So this is what we get, and this is something that we are going to use. This is what we have used before also in the time domain, but now we are going to use it explicitly in the frequency domain. Because at the end of it, we want to talk about spectrum, and most of the time we look at things in the frequency domain. There is a pulse, which is the time domain. So you get something, but you want to know what is the frequency behavior of the pulse. So you need to know in the frequency domain. And the shape of the pulse, the shape of the frequency spectrum, these are all the things that we need to understand, or try to figure out why the shape is like this, whether there is a delta functions pulse, whether it's a continuum pulse, whether a continuum actually is a continuum, things like that. Now, when I do this thing, just as an aside, let me also tell you that the results that we gave, remember, we started with a Lorentz gauge, and the Lorentz gauge basically enabled us to write down the phi and the a in terms of the four-dimensional Green's function. So give us this D'Alembert of phi. So make the things very simple.
Sir, can you explain the highlighted statement once again, that why in the frequency domain is it of this one?
See, remember B is equal to n cross E and E is equal to minus n cross B that we got before when we didn't.
Yeah. That is in the real space,
yes.
Spatial.
In the frequency space also you get the same thing basically when you do this. So if you come from over here, you will get this answer. So if you go over here, I omitted 2-3 steps over here. So you basically go to the E over here at the top of the screen. These two terms, you make it into one term. When you make it into one term, you will find that it comes like this. So it comes like this. Okay. Yeah. Then from here, you will see that you will get it in terms of
yes.
N cap. So there will be a 1 minus n cap term will come and all.
Yes, I got it. But why it's obvious? I mean that
Because you could have taken the frequency domain result and then just did the Fourier transform, you would have got this, right?
okay.
This is something like just हाथ घुमा के ऐसा किया, but there is a reason to this हाथ घुमा के करना, because some of the stuff that we did inside, some of the intermediate steps will be used. That's why.
Yeah. Thanks.
Now, this whole thing of this Green's function approach was applicable because we could write down, as I said, the Green's function thing, this 4-dimensional Green's function approach to solve was done because for both phi and A in the Lorentz gauge, we got this D'Alembertian equations, right? Which was very similar. They were exactly the same in the Lorentz gauge, right? So what was the Lorentz gauge? The Lorentz gauge was this, right? This is a thing which we applied. This is a gauge condition that we applied. We started with the gauge condition for A and phi separately. If you go back, you remember how the equations were. Then we got some complicated equation for phi and A, which had this kind of term in between. And when we applied this gauge condition, we got this 2 D'Alembertian, which was very simple. Okay, so this was the Lorentz gauge equation. Now, we also showed that when we use the D'Alembertian on the Lorentz gauge, so this is LG means Lorentz gauge, okay, that was 0. And that basically comes from the fact that when you impose an equation, when you impose some gauge condition, it's not an arbitrary gauge condition. It has an underlying meaning, and this Lorentz gauge is a consequence of my charge conservation, divergence of G of del rho del T. That was 0. And so this is why the Lorentz gauge condition works, and we got this kind of results. Okay. Now I can Fourier transform my Lorentz gauge equation. So this was this divergence of A1 by C. So I can Fourier transform this. And what I will get is basically, I will have a divergence of A. This was in R and T. So I will get in R and omega. And I will get 1 by C del phi del T. But remember, when I do a del T, I will get a minus I omega. So I get a minus I omega by C del phi del T. So plus becomes minus, with this minus I omega coming over here. So we'll end up, we'll have this term over here. And of course, everything will be in the frequency domain. Okay. So what I will end over here is an equation like this. Okay. I can take this out. I can bring in the K cap in. K cap was omega by C. I take that out. I can I cap, and I will have an equation which is this, which basically tells me that my phi from this, because this is equal to 0 because Lorentz gauge was 0. So this basically tells me that because whatever is in the bracket should be equal to 0, because I can, this is applicable for every K cap, which basically means my phi, that is my scalar potential in the frequency domain, is that n dot my vector potential in the frequency domain. It's a beautiful, nice result, right? So in this frequency domain, the scalar potential is n dot the vector potential. And this actually, if you go back, if you look at how your E and B are related, this thing basically gives me back this whatever is there at the top of the page now, that my E is n cross B minus n cross B. And you can see this is can be done from over here also. So this beautiful result is self-consistent. There's something that these are basically small self-consistencies, things that is there in the structure of the EM theory, which one is interesting to see. Okay. Now we have got my E and B. Okay, we have got this E, I have got this B. Anyway, this horrendous equations. I mean, not horrendous enough, but the equations. And what we want to do is basically we want to calculate the flux. Okay, because we ultimately want to go to power. To get the power, we need to know the flux. So we'll write down the flux. So the instantaneous flux, this comes from your Poynting vector. So it's C by 4 pi ERT BRT. Okay. Now we want to go from, obviously we want to go from this equation of course was in the time domain. We have to go to my frequency domain. So this is straightforward. I integrate if I want from this instantaneous flux, if I want the total radiated energy, just like my instantaneous energy in a particular time, then I have to integrate over this time. So one of the things I want to say over here is that the reason we are doing this thing is that at the end of this class, we want to go beyond results which talk about total radiated energy or things like that. Because at the end of it, we really do not have anything where we integrate over that all the time period. I mean, we are not going to, in practically, when we are going to measure something, we are not going to look at a huge enough time period going from minus infinity to plus infinity. So we have to think of some other way of looking at fluxes. So that's where we are leading to. So over here, we have this instantaneous flux, okay, which basically, this is the formula that we always know. Then from there, we can calculate the total flux, okay, which is per unit area. So we integrate this. And when I do this ERT and BRT, I can now write in terms of the frequency, but integrate over the frequency. Because remember, your F and FT and F omega was related. So that's what I've done over here. Okay. And integrate over frequency. And very quickly, we find that the total radiated energy per unit area, that comes out to be this relation. So the total radiated energy per unit area has the direction, okay, unit area, the area is perpendicular to the propagation direction, the unit area perpendicular to the direction of propagation, and has this form where I want my BR omega, and I have my BR omega over here. BR omega is over here, modulus of that squared, okay, and then that's integrated over d omega by 2 pi. So your integral over time is over here. There's an integral over frequency. Obviously, that if it's total energy, then in the time domain you have to integrate over time, and the frequency domain you have to integrate over frequency. Okay. So this tells me that if I want to take this integral, okay, n cap dot SR, so put an n cap over here. So this SR is over here. Okay, we put an n cap over here. So I want to take basically the flux flowing out of an area which is perpendicular to the degree of, to the direction of propagation. And remember that my solid angle is ds by r squared. Okay, remember this. So then that is basically this formula. It comes up to be this. Okay, so this is what we have. Basically reading the same formula above. Okay. So what we have had over here is that if I want to calculate the total energy propagating out over a unit area perpendicular to the degree of direction of propagation, then that is given by this integral over the frequency domain of BR omega squared. The frequency is integrated from 0 to infinity. Given this, this is your final homework. So when I'll give you your homework tomorrow, these two homework will be here. So maybe you should write it down and start. Given this, I can ask you to calculate this. So remember, this is basically your flux. So coming from your energy per unit time, and then also energy, total energy per unit time, per unit area. If I want to calculate the energy per unit frequency and per unit solid angle, then starting from over here, so basically using whatever I have written over here, okay, and whatever I've written before in this region, So one can try to show that my energy radiated per unit frequency per unit solid angle in the direction of n cap is this quantity. And this is a very important quantity that we will use again and again. Okay. So this is omega squared by 4 pi c, 4 pi squared c, and then there is modular squared of the current, and there's a modular square of the charge density. This thing. So this is something that you should calculate. It's not a big calculation. It's 5, 6, 7 lines calculation of that order. Okay, you should do that. So this is an important formula that we're going to use. Then we can, in fact, try to write down a dipole formula from this quantity by taking into consideration that, remember, dipole is when charges were local and we are looking far away, that you can consider this local distribution of charges as a dipole. So the typical length over all the charges, if that is a and that is much, much less than lambda by 2 pi, in that limit, you have omega by c n cap dot r prime that to be less than 1. And if that is less than 1, then remember there is an exponential which has this term. That exponential basically becomes 1 unity. So this exponential, which was always there in phi and a or whatever, that exponential becomes unity. And in that sense, when this exponential unity, so in this condition is supplied, this phi and a can be simplified. And then you can show that this equation, this energy radiated per unit frequency, that basically gives your old Larmor formula, exactly what we did before, except that over here, my dipole is basically in the frequency domain. So it's a d dot omega. Previously, it was not a d dot omega, it was a d dot t. Remember that. Now it's a d dot omega. So the frequency domain. So these two are two homeworks that you should do. And we are going to use without, so this is your work for the homework, but we're going to use the equation over here to go to the next part that we want. So next part, of course, I have not written down, so I'm going to write down the next part. So this way I sort of, cram a bit more instead of writing everything. So some part I'm going to write and some part is written before. So as I told you in the very beginning, one of the thing that we want to do today is to try to build the states so that one can go to specific forms of radiation, which is, as I said, Cherenkov or synchrotron or X-rays in the next few classes. Now, these are radiations which are observed. So we observe this radiation. But what is observed is observed in some time period, right? So you do not have a detector that keeps on observing for infinite amount of time. We are going to have a detector, we're going to observe it. So whatever is observed is for a specific time period, some length of time. In that sense, we have to basically look at everything that we have, which is this equation that we have over here, this energy radiated per unit frequency, all these equations. These are, remember, these are like the power spectrum. These are basically related to the power. We must calculate, or we must have a formalism to calculate this, which is sort of an average over some specific period of time, because that's what we're going to observe. Okay. Now, what is the specific period of time? How you calculate the average? That will depend from your case to case. So if you want to do Cherenkov, maybe if something is very fast in a circle, maybe my time period will be something different. I mean, we have to think of that case by case basis, but we first have to start with some general formalism. So what we want to do now, basically, we want to calculate basically, or try to establish what we can call some sort of an average time period. Okay. So let us start with the homework problem that we have. Remember, in the homework problem, that the first homework problem, we were asked to show that this energy, it goes away per unit frequency per unit solid angle. That was omega squared by 4 pi squared c. And then there was a current term and there was a charge term, which was 1 by c g cap k cross omega whole square minus rho the whole squared. And this obviously comes from your E field. Remember, the E was, E had these two terms over there. And this can also equivalent be written, basically E and B, remember over there, can be written like this, omega squared by 4 pi squared c. And I can write down basically n cap cross I think this is fine. Yeah, I think it's fine. Okay. Now, this is a general expression for the spectral distribution. So energy per frequency per source. So this is what I will call a general expression for spectral distribution.
Sir,
Yes.
there should be a c square in the upper.
I also think there should be a c squared. But I'm just wondering whether the c squared cancels somewhere. I also think there should be a c squared over here because this. I think the c cube will come over here, and I think a c cube will come on the front, and then
Yeah, c cube. So
okay. So this is for the general. So it's energy per frequency. Okay. Now, as I said, this applies to radiation at all times, right? This applies to radiation at all times. Basically minus infinity less than t less than infinity. Okay. Now, what we want to do is want to find an expression for a limited time period. So we want to find expression for a limited time period. Okay. So that basically means I would have to take some sort of averaging over which I want to average this first equation, which was this this equation. Okay. So what I want to do is I'm going to write down the previous equation like this. So I'm going to write the second part of this first equation. I'm going to write it in terms of, because it's a modular square, you write it in terms of two parts. Okay. So I'm going to write it down like this. So my d2e d omega d solid angle, that is going to be very where is it? Omega squared by 4 pi c cubed. Yeah. Omega squared by 4 pi squared c cubed. And then there will be two terms over here. One will be n cross So this first term over here, this is basically n cross j times n cross j. And then I'm going to change this j k omega in terms of e to the power I omega t. So I want to bring in that t again because I want to play around with the time period. So what I'm going to do is that n cross dt e to the power I omega t j cap, and now instead of k cap omega, I'll have k cap t. This thing star another n cross, then there's a dt prime e to the power I omega t prime j k cap t prime, and then this. Okay. So now we have, look at the integral. So now let us focus on the time integrations. So look at the time integration. So if I look at the, if you look at the time integration, what we have something like this. We have a dt, we have a dt prime, and because of the star, okay, I will have, I can put in a minus and then put the minus outside. So what I can have is basically e to the power minus I omega t minus t prime, and then there's a j k cap t star, and then j k cap t prime. Okay, this is what we have. Right? So we have this t minus t prime that is coming over here, and we want to utilize this t minus t prime. What we're going to do is we're going to introduce two new times. Okay, so introduce, okay, first we introduce the time difference, okay, t minus t prime. This I can introduce. Let me pat it down nicely. Introduce this new quantity which we called tau, which is the time difference, t minus t prime, and we introduce an average time, because the two time scales that is there is t and t prime. T minus t prime gives a time difference, and I can also introduce an average, which is t, which is basically t plus t prime divided by 2. Okay. So then what we have is basically my dt prime. This basically goes to dt d tau. Okay. So I can rewrite this equation, which is the integral of these two time periods. I can rewrite this like this. Then we have an integral over and some average time t over some time difference tau e to the power minus I omega tau. Okay, then j k cap t plus tau by 2 star j k cap t minus tau by 2. So something very interesting has happened over here, as you can see. Okay. So first thing that we should realize over here, that in doing this cross correlation, so in doing the amplitude squared, we have this cross correlation of between these two terms, which is t and t prime, and that has led us to two new time scales, one which is the average time scale and one which is the difference time scale. The first of one is this one, okay? So this is basically tells you that anything important, range of the tau contributes is 1 by omega, right? So from here, we can show that the important range, okay, of tau, which contributes is basically tau equal to 1 by omega. Okay, that gives you the, so if there's a frequency which is being emitted, then that frequency and tau has to be related like this. So this in this process, whatever is a physical process, this sets the time scale of emission. Okay, so this basically sets the time scale of emission. For example, for ordinary light, I know what the frequency is, approximately a few thousand angstroms. So for ordinary light, okay, for ordinary light, tau will be of the order of 10 to the minus 14 to the minus 16 seconds. So 10 to the minus, let's say, 15 seconds. Okay. So this is the time period in which the real physical process happens. So in fact, if, for example, if there was a multi-level system in which some light was coming out, there will be some excitation times for these two, okay, and the difference would give you this kind of time period. So this is the kind of time scales in which the process is happening. Now, this of course is a very, very small time period. So we are not going to have a detector typically in general, which will be looking at time scales of this time period. We'll be looking at time periods which are much larger. Okay. So that time period in which we look at this phenomena, that is given by the, so this is a microscopic time, right? This is microscopic. Whereas my t is a macroscopic time. Macroscopic average time. Okay, this is the average time over which lots of emissions have happened and we are detecting it. So when we are going to look at power spectrum of our process, we are going to find out what is sort of this microscopic power that we are getting, but it also needs to take into account whatever the process is going on, which will connect it to the microscopic time. So if I put all this, whatever I said together, then putting together, okay, what I can define is my, whatever was this spectrum, okay, this is basically something like this. So this part is basically the power spectrum or the flux, whatever you can think of, power spectrum at time t. And if we integrate this over this time period, we get whatever the spectrum that we are going to observe. So with this definition, we can write down what is my d2p d omega, d small omega, so d frequency, d solid angle is write it down. So that will become is a very, very important equation. Okay. This will be omega squared by 4 pi squared c. So I'm taking one c inside. And so then this will be integral over d tau to infinity. Doesn't matter, but d tau, remember, is a very small region. So this minus infinity doesn't matter that much. E to the power minus I omega tau into n cap cross 1 by c j cap t plus tau by 2 star dot cross c j cap t minus tau by 2. And one can write this another way, just by going to this first formula where it is written in j and minus. So one can write it in that way also. Okay, so this is also equal to minus infinity to infinity, and hold on. Omega squared by 4 pi squared c infinity d tau e to the power minus I omega tau multiplied by 1 by c j cap j t plus I'm hurrying and so doing also some mistakes. K t plus tau by 2 star into 1 by c j cap t minus tau by 2. This thing minus rho q t plus tau by 2 star into t minus. So this two formula that we have, these are the two formula that we're always going to use, okay, when we are going to calculate any specific form of spectrum from any radiation. And we will see how very nicely there is some physics that comes in as you identify what is this d tau, what is this t, how to identify d tau, how the spectrum physically relates to d tau, and how that d tau, remember, relates to an omega. Okay, so how these omegas of the spectrum will be connected to omega of the process, which gives the spectrum, things like that. So this is an important relation that we're going to use again and again, and we will sort of stop over here, because after this I want to go into applications. Okay, so the whole idea of today was to basically derive an average spectrum and introduce timescales, two new timescales in the spectrum. Okay. One with the phenomena itself and one with the period of observation in some sense. This will become clearer when we take into account, when you go into real particular examples, especially when you go into synchrotron radiation, you will see how very nicely this tau and the big T, these two times from the figure or from the physics, these two times are defined and how they are related to the physics of synchrotron radiation, and how that is related to the spectrum of synchrotron radiation. So a couple of classes. We'll come to that. Okay, so that's where we stop today. And yeah, thanks for coming on a Sunday so that we could bridge this gap. And hopefully in 3 classes, we'll try to be as much as possible. Again, I'm going to write down at least part of it my lecture, because that will help in doing things fast. Otherwise, it takes a long time. We are coming to the end of it, and I hope that's okay with you guys. Okay. So thanks. You guys can now.
Sir.
Who is it? Amit? Yeah, Amit.
Yeah. And sir, I have joined a bit later. So, what is the date that is fixed for the MSM take-home exam?
After the so presentation, a couple of days after the presentation.
Okay, fine. So it's in June.
It's in June, yeah. We have to finish by June. So we are supposed to finish by 15th, but we are not finishing by 15th. We're going till 30th. And that's all because in the beginning, I was a little lax, to be honest. I think it's my fault that I was a little lax in the beginning. We're doing things slow. But yeah, so we have this 15-day gap, 15-day delay with most courses. I don't know how many courses are going till the end of June, but I know StatMech is going till the end of June. I don't know what other courses. Okay. Yeah, you can stop the recording, and then if people have other questions, you can ask.
Sir, exam will be offline, right?
Exams will be offline, online, I don't know. I mean, it depends on what is. So if,
But if offline, then how many hours will be given?
see, if I give you a take home, which is what you call offline, then I would hopefully I'll give you the whole day to work out and give back to me.
24 hours.
Yeah, I would, don't creep about 24 hours or 19 hours of thing. It's a whole day. I give you in the morning, you give me at the end of the day. If you have not done anything by 18 hours, then not going to do anything by 20 hours.
Yeah. Thank you.
Or the other option, as I said, is in 1 hour. I mean, I would really talk to Vaibhav and try to see that if he's okay with not having a final exam, then that's it. Basically, all depends on your mid-sem and your basically your presentation will be counted as your final exam. But if Vaibhav insists, which he has done before, that no, even last time he insisted, no, we have to have a final exam, then my hands are tied. Okay, so good. Thanks very much. You guys can now go and go. I think Sunday people said they want to go and have biryani, so now you can go and have